All right. When our just to recap in case the video cut out there. So when the first derivative is equal to 0 and goes from positive to negative, then we know the original function is going from increasing to decreasing, which means you've got a relative max at that particular point. When the derivative is negative and then goes positive, then the original function was going from decreasing to increasing, and at that particular point you have a
Relative minimum.
relative minimum. And that is the first thing that we're going to be discussing today, and that's what we're going to be looking at. Okay. If you remember, the kind of this whole discussion is kind of brought about by the fact that way back when they didn't always have calculators, and sometimes functions are really hard if you don't have a calculator to graph it to see where it's increasing and decreasing, stuff like that. But the derivative is normally a little bit easier to manipulate. The derivative is normally a little bit easier to look at and kind of get your mind wrapped around, and then also do some algebra on. But nowadays, a lot of the stuff that we have, we can just graph it and then just have the computer run the numbers, on things like that. But it is helpful for other situations as well. So we'll go ahead and do this. Just to kind of get a little more aware of what's going on in the relationship between the function and its derivative. All right. For each problem, find all points of relative minima and maxima. Okay. So the process, if we're going to apply this fact right here, what we're going to do is we're going to find the derivative, set it equal to 0, and then find out what's going on a little bit before and what's going on a little bit afterwards. Okay? So let's go and do that. F prime of x is equal to, call it out to me, class.
Negative 4x plus 8. So
4 plus 8. Now, if you, what we did earlier is we kind of sketched this. I mean, I guess we could, if we wanted to, we know it's going to be. Anybody know what that graph looks like? Negative 4x plus 8.
Y-intercept is at 8, and then it has a slope of 4. Negative 4.
Yep, slope of negative 4. So it's going down, something like that. This is the graph. This is f prime. Okay. So it clearly hits 0 at some point. We could probably reason through when that happens. Negative 4x plus 8 equals 0. Subtract 8 from both sides, and then divide by negative 4. It looks like it occurs at 2, right? So if I were drawing a sign chart, I would have 2 right there. That's my, what we call my critical point. It's the spot where the derivative equals 0. Okay? And what we're interested in, so I'm going to put f prime right there, in what's going on a little bit before and what's going on a little bit afterwards. Now, in this case, since our derivative is so easy and we even have a graph here, we can do this very quickly. A little bit before 2, so pretty much in this region right here, I'll just put 0. That's kind of easy. We know that the derivative is positive, and a little bit afterwards, maybe we'll just say 3. We can tell here from the graph, or we could plug in a value. 3 times negative 4 is negative 12, plus 8 is negative 4. We know the derivative is negative right there. That tells us that the original function is doing what in this region right here?
Going up and down.
So it's increasing and decreasing. And then, like I said, applying this knowledge, that tells us that at x equals 2, we have a relative maximum. Are there any relative minimum?
No.
No,
Because you didn't give us one.
because it's increasing from negative infinity up here, and it's decreasing afterwards, after 2. So it's not gonna turn around and be sneaky on us right there. That's it. That's the whole story. All right. So for our answer, we would say there's a relative max at. Now they say find all points of relative minimum and maximum. I guess we need to put the x, y pair. So I'll say 2, comma,
0.
no. That would be if I plug 2 into the derivative. I need to find what 2 is on the original function, because that's going to tell me what's going here. So negative 2 times 2 squared plus 8 times 2 minus 5. So that's 4 times 2, negative 2, so it's negative 8 plus 16 minus 5. So negative 13 plus 16, so it looks like 3. Relative max at 2, 3.
Nice.
Yep. Now, could we solve that using some quick calculator tools? Absolutely. Just kind of showing you how to do this stuff with calculus. If you think about it, what does this graph look like right here, class? Negative 2x squared plus 8x minus 5. Say again?
Parabola.
It is a parabola. What else do I know about it?
It's down.
It's opening downward. How do you know that?
Because it's negative.
Because this is negative? So, how do you know that? Did somebody tell you at some time that if that first number right there is negative, then
I
it
think
opens
so.
downward? Yeah. And if it's positive, it opens upward? Okay. Pull out a sheet of paper. Let's talk about that just real quickly. Okay? Because how did they know, right? That
That was actually correct.
that's actually correct, right? Or how do we know that that's correct? So quick little side problem right here, okay? F of x equals ax squared plus bx plus c. And we're going to say a is positive, a is greater than 0. This is the generic quadratic, right? Okay. So you're telling me that if a is positive, like I'm saying right here, which way does it open?
Raising upwards.
Up, like a cup, right?
And then the frown down.
Frown down, right? Okay, but it's not frown down, it's up like a cup, okay? So what calculus information, like what does calculus say about up like a cup?
It's positive.
What is positive?
The second
Derivative.
derivative.
The second derivative, okay? Let's take the derivative of this, and then we'll take the derivative again. So what's f prime of x?
2ax
Keep going.
plus b. And that's it.
That's it. Somebody else? What's the second derivative?
2a.
That's not somebody else, but thank you, Hector.
Well, that's good.
2a. Now, if a is positive, what can you tell me about 2a? It'll also be positive, okay? So 2a must be greater than 0. So if I were doing a number line, and this is the second derivative is always positive. Therefore, the original function is always
Positive.
not positive, concave up. Does that make sense? Think about it with the same way. What if a was negative? Then you would have a negative right here, and this would also be, and the derivative of, you just pull that 2 down, you have negative 2a. The derivative of negative 2a would be just negative 2a. Therefore, if a is positive, then negative 2a would always be negative. If you had a negative right here, then it would be concave down. So calculus sort of verifies what we have always been told, that if that leading coefficient on the quadratic is positive, then you're opening upward, and if it's negative, you're opening downward. Okay, that was a fun little diversion. All right, let's go ahead. We'll do this one together. So number 5, finding the points of relative minima and maxima. So we'll look at the derivative. Call out to me the derivative there, class.
Negative 3x squared plus 6x.
Now, if you wanted to, we could graph this, okay? But we might be able to do some of this on our own. What we're interested in is where this is our first derivative, equals 0. So let's go ahead and do that. Now I've got some techniques available to us. We'll factor out I'm going to factor out negative 3. If I come back around negative 3x.
It can be x plus 2.
X minus 2 is that what you said?
Yeah.
Because if I factor out negative 3, that's 6 becomes a negative 2. So I have negative 3x equals 0, which means x equals 0. Or x minus 2 equals 0, which would mean that x would equal 2. So when I draw my number line here in my sign chart, I've got 2 points of interest. These 2 critical points rather, 0 and 2. That's where the derivative equals 0. Now I need to figure out what's going on a little bit before and a little bit after on each one of these to figure out if this is a relative maximum or a relative minimum. Okay? So I need to pick a point a little bit to the left of 0. I say, negative 1 sounds good. Pick a point between 0 and 2. 1 sounds good. And pick a point a little bit after 2. Alright? So ladies, you take care of the negative 1, since I know you're all going to pay real close attention to the negative in the parentheses. Okay? Guys, you take care of the 3. And I'll take care of the 1 because I don't have a calculator on me. Now what are we plugging these numbers into? The derivative, that's right. Negative 1 is what? Stephanie and Emily, we need y'all to verify.
I got negative for 3. Not 5.
Okay, so you have you're saying you have a negative number, Hector?
Yeah.
Okay. I mean, if I put in like a million, it'd be negative 3 times a million squared equals 6 times million. That term's going to dominate. So I would go on that. All right, Nick, what does that tell us about the original function in this region right here?
That it was decreasing.
Decreasing?
Then increasing.
And
decreasing.
Hey, so we have a spot where the derivative equals 0, and we're changing from increasing to decreasing. I think we definitely have one from decreasing to increasing, one from increasing to decreasing. We definitely have a relative minimum and a relative maximum. What's this one right here going to be? Going from decreasing to increasing? That's a relative min. And from increasing to decreasing, we have a relative maximum. Great. Okay. So, at this point, I'm just going to let y'all use your calculators, although we don't know if we really need it. This is coordinate 0, and we plug it into here, 0, 0, negative 5. That's not too bad. 2, negative 1. I'm going to need validation on that. Okay, validation here. So, we'll summarize our information here. Relative minimum at 0, negative 5. Relative maximum at 2, negative 1.
I was wondering, whenever I was looking over this weekend, I was wondering if we could go over how to take the derivative of, like, number 6. There's another one on
Yep,
15 and 14.
absolutely, yeah, something like that. Let's go
I don't know
do
if
it.
we've been over that before.
Well, let me make sure we get the answer right. 0, negative 5, 2, negative 1. Good job, class. Yeah, because pretty much for your homework, you're going to have to do what we did on the first problem on 1, 2, and 3.
K-rule?
Yes, hold on a second. Yes, I'm talking about like in the future, like for the rest of these other problems right down here. Like these, I'm going to say find where it's increasing and decreasing, which we did. X-coordinates of inflection points, we'll talk about that in a second. Open intervals where the function is concave up and down, we'll also talk about that in a second. Relative maximum, minimum. So actually, 1, 2, 3, 4, and 5, and 6 dealt with increasing, decreasing, and relative maximum and minimum because we found the derivative And actually, if you find out where it's increasing and decreasing, you also, sort of as a bonus, find out where there's any relative maximum, relative minimum, right? So that's really not too much different. But we do need to talk about the concavity. And specifically, how do we deal with problems like this? And you said chain rule. I think you mean quotient rule.
Yeah, that's what I want.
That's what you meant. Okay. Yes.
That's what I want.
So, yep. I'm going to push that negative up here to the 2. Anybody remember the quotient rule phrase?
It's not the high D. High D low.
Low D high.
Low D high, but high D low.
Almost.
Mine.
It's. I'm going to say it right so because you hear all this wrong. Just say it right. Low D high minus high D low over low squared. We got here. So low, that's x squared minus 9. D high, what's the derivative of negative 2? 0. Minus high, so negative 2. I'll make it negative 2. Notice I'll put it in parentheses because this minus here is part of the formula. D low, what's the derivative of x squared minus 9?
2.
Over low squared we go, so x squared minus 9 squared. So negative times a negative is positive, so it looks like we have 4x in the numerator and x squared minus 9 squared in the denominator. We did do a problem similar to this on Thursday. What's been our general procedure at the next step, or at this point? What's the next thing to do? Find where the derivative equals 0. That's this right here. Yep. That's going to happen when you have a ratio like this, when the numerator equals 0. Okay? Because it's whatever. If this equals 0, then anything 0 divided by anything is 0. So 4x equals 0. So that's going to occur at x equals 0. But if you remember, our critical points are the points where that increasing, decreasing can change. It can also occur when the derivative does not exist. Okay? So when I'm finding my critical points here, it's when the derivative equals 0 and when the derivative doesn't exist. Now, those previous two problems, the quadratic and the trinomial problems, we didn't have any place where the derivative didn't exist. But on rational functions, we do have a situation that is the denominator equals 0. That's going to occur when x squared minus 9 equals 0. That means x squared equals 9. When does that occur? When x equals
3.
Almost.
3,
Plus or minus. Yeah. This is one of those cases where it actually does make a difference because we now have 3 critical points. We have negative 3, 0, and positive 3. Negative 3, 0, and positive 3. And at this point, frankly, I'm just going to say, let's go ahead and use a graphing tool to help us out here, namely Desmos. So 4x over x squared minus 9 squared. And then that will help us figure out what's going on in those regions. So 4. Y equals pretty good, y'all?
Yeah.
So if you look at negative 3, we have a situation. So this is the derivative. Okay, so we're graphing the derivative, and we see that at negative 3 it doesn't exist. At 0 it crosses the x-axis, also crosses the y-axis, and at positive 3 there's another spot where the derivative doesn't exist, which is kind of what we were expecting. Okay. So looking at this, in the region to the left of negative 3, is the derivative positive or negative? So there's negative 3, and this region over here, is the derivative positive or negative?
Negative.
Negative. What about from negative 3 to 0?
Negative.
Negative. From 0 to positive 3?
Positive.
And then from 3 to infinity?
Positive.
Positive.
So what is that?
Well, we've got a decreasing,
Decreasing.
a decreasing, increasing, and increasing.
So that's a relative minimum.
Say that again?
A relative minimum.
A relative minimum. Yep.
And the decrease.
Right there is 0. What about a spot where it goes from decreasing to decreasing?
It's just absolute. Never mind.
It's a nothing. I mean, there's not a relative maxima there. Okay, it's a candidate. It's a critical point, really. But there is no relative maximum. In fact, there's actually an asymptote there. Okay, because it also doesn't exist on the original function. So yep, looks like we have a relative minimum. And if you plug in that value, anybody go for it? What do we get? A y value there. Plug in 0 onto the original function. Negative 2 over 0 minus 9, so 2 ninths. So our summary is relative minimum at 0, 2 ninths. Good for us. Would you like to see that original function and see what it looks like on Desmos?
Yeah.
Alright, original function, negative 2 over x squared minus 9. Alright, let's see if this matches our expectations. Between 0 and negative 3, is our function decreasing?
Mm-hmm.
Yep. What about from negative 3 to 0? Is it increasing? Or sorry, is it decreasing? Yep. Relative minimum at 0, yep. 0.22222, if you're familiar with your 9 fractions, that's 2 ninths. And then from here to 3, it's increasing, and then asymptote here at positive 3, and then we can see from 3 onward it's increasing. It's increasing, but it's asymptotic here. It approaches, the y values approach 0, but they never actually hit it. It just keeps rising and rising. So, some interesting information there with the calculus. Alright. This is the third set here. Cody, go and read to us the instructions on this.
For each problem, find the x-coordinates of all points of inflection and find the open intervals where the function is concave up and concave down.
Alright. Class, how do I know when a function is concave up and concave down? Increasing and decreasing.
F prime.
Yes, unfortunately it's really hard to do analysis on where a function is increasing or decreasing. What's helpful to go actually is to go even deeper and to look at that second derivative. And when is the second derivative positive and when is it negative? So let's play the game. I mean, we can probably make a guess based on our pre-calculus knowledge. Is this function concave up or concave down? Let's verify that with the second derivative. So here we go. F prime of x is equal to 4x minus 8. Second derivative is 4. You're going to love this. So this is what's called a second derivative chart. Okay? Now, what we normally want to do when we're looking at the second derivative, we want to figure out when is it going to equal 0. Well, guess what? Does the second derivative ever equal 0? No. So I don't have any, what you would call like critical points or possible inflection points on this one. The second derivative is just always 4. So it doesn't matter, I mean, so it's not like there's a point here that I need to go to the left. There's nothing, it's always 4. The second derivative always positive. It's always positive 4, rather, right? So, skip over f prime. What does that tell me about the original function, f? It's concave up everywhere. From negative infinity to positive infinity. So if we were to write our summary sentence, we would say concave up from negative infinity to positive infinity, concave down, never. Inflection points, none. And that problem matches our expectations of something with a leading coefficient of positive number. Nick, any questions? All right, now for something a little bit more interesting, right? A cubic. We'll just go ahead and do that same analysis. First derivative class. So you can see what you're going to do for your homework is you'll do a quick little stop right here on the first derivative, and you'll set that equal to 0 and find where it's increased, positive and negative, and that's where the original function is increasing, and all blah 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 blah, all that stuff that we've just been doing. And then you'll go on to here and you'll do the second derivative, and we need to figure out where the second derivative equals 0. No big deal, that's just going to occur at 6x equals negative 6, or sorry, positive 6. So at x equals 1. That's our, what we would call, this is a possible inflection point, okay? So we do that same sort of analysis. We say, all right, interesting point is 1. We want to figure out what's going on with the second derivative a little bit to the left of it, maybe at 0, and what's going on with the second derivative a little bit to the right of it, maybe at 2. I'm going to label this very clearly f double prime. Let's plug in 0 to this. 6 times 0 minus 6, so that's 0 minus 6. Some negative number. Plug in 2. 6 times 2, 12 minus 6. 6, which is positive. Which tells me that the original function. Nope. That's what you're saying is if this was the first derivative. Now we're looking at the second derivative. Somebody else? What does that mean up here?
That
You're right with the concavity, but this is negative. So concave down. And concave up.
We can have both of them?
Yes.
Would one also be the inflection?
Mm-hmm. So if we write our summary sentence here, it is concave up from 1 to infinity, concave down from negative infinity to 1, and there is an inflection point at 1, and they want to probably us to give the coordinates, so I'll plug it in here. So 1 cubed, which is, so I'm plugging into the original function here. So f of 1 equals 1 cubed minus 3 times 1, so it's minus 3 plus 6. So inflection point at 1, 4. Oh, they just say, do the instructions say the x coordinate? Well, y'all could have remembered. The x coordinate of all the points of inflection. So there we go. to find the second derivative. Are y'all ready for this? Let's do it. Hardest problem you're gonna have to do, find the second derivative of a rational function, but this is a good practice for us on our quotient rule. So Jeremy, call out to me here, quotient rule.
4x plus 8 times 2x minus x squared times 4 divided by 4x plus 8 squared.
That's low d high minus high d low over low squared we go. At this point, it's going to be advantageous for us to do a little bit of algebraic simplification. Alright, so let's go ahead and do that. I'll distribute the 2x. So we've got 8x squared plus 8x, plus 16x minus 4x squared all over. Denominator is fine, 4x plus 8 squared. So combining like terms, we have a 4x squared plus 16x all over 4x plus 8 squared. That look about right to y'all? Alright, here we go. Second derivative. Alright, class. Low?
D high.
D high, okay, so call it, what's low?
4x plus 8 squared
D high?
times 8x plus 16
Minus?
4x squared plus 16x.
I'm going to put that in parentheses. D low. Bring the 2 down? Yeah, we're going to do a chain rule on this one. So 2 times everything inside intact, 4x plus 8, then to the first, okay, pop down, power down,
And then
times the derivative of the inside,
4. That's a big old boy.
over
4x plus 8 squared.
squared. Low squared we go. So we already have, so it's going to be 4x plus 8 to the 4th.
That's huge.
Yeah. At this point, if we're gonna, it's just, we seem to have traded what was a pretty basic problem for a more advanced problem, but that's kind of the way it is on this one. Let's go ahead and use technology to do the positive negative sign chart on this one. Sound good? Alright, so F double prime. I would use Desmos on this one. Alright, so y'all make sure I'm typing this in proper here. So y equals, do the denominator first. This is the easy part. 4x plus 8 to 4. Alright?
Oh, you
But
put
with 2.
2. Ah, you messed it up.
Alright, I messed up the easy part here. Alright, so 4x plus 8 squared times 8x plus 16. Kind of interesting to see it kind of take shape. 4x squared plus 16x. Alright? Times 2 times 4x plus 8 times 4.
Dang.
Is that looking right?
What is that?
So what are we looking at here, class?
Mr. Goddard, you had a flip parentheses, so I don't know if that messed it up somewhere. Back that way.
Let's shift this over.
Or is that right?
Nope, something doesn't look right.
One by the two.
This,
Yeah.
what in the world is that?
That's supposed to be 4x plus 8 times 4 and times 2.
Like that?
Yeah.
Yeah, but you don't need the parentheses next to the 2. That
I
one.
like this one.
Yeah, and so then that outside one, yeah.
There you go, that looks better.
Way better.
Okay.
Oh.
Is it ever crossing the x-axis? Looks like it's just,
It's even.
yeah, that just means it's so close to 0 that you can't even tell. Huh. So I'm looking at the second derivative, I'm looking at places where the second derivative is 0 and places where the second derivative doesn't exist. I'm not seeing it equal 0 anywhere, are you?
No.
Do you see anywhere where it doesn't exist? I'm seeing one place where it doesn't exist.
The asymptote.
Yeah, that asymptote. If I were to make a guess, I would assume that's where 4x plus 8 equals 0. 4x plus 8 equals 0 when x equals -2. So looking at that graph of the second derivative, what do we see in this region over here? It's negative, and then over here it's positive, which tells us that the original function is concave
Down.
down,
Up.
and over here, it shouldn't be that difficult. When we're talking about second derivative, we got concave. We're talking about first derivative, we're talking about increasing, decreasing. Okay? Does that mean that -2 is an inflection point?
Yeah. It's impossible.
Not necessarily. The problem is, the reason why, as it turns out, it is not an inflection point, because if you look at the original function, if you plug in -2, then you're going to get 0 in the denominator. Okay, it's a point where it does change from concave up to concave down, but it's not an actual point of inflection because it actually doesn't pass through that point. Okay, so you're like, what do you mean by that? Well, let me write down the equation here. X squared over 4x plus 8. So we're saying that concave down, concave up.
So it just keeps moving.
Whoops.
Oh, that's where the asymptote is, right?
Yep, there's an asymptote right there, -2. Is our graph concave down to the left of that?
Mm-hmm.
Is it concave up to the right of it?
Mm-hmm.
Yep. So, so we would say our answer is concave up from -2 to infinity, concave down from -infinity up to -2. Inflection points, you might say, oh yeah, it's inflection point -2. No, it's not, because inflection point has to actually be a physical point on the graph.
So
And -2 does not exist on our function. So, none. Alright, we have now given a function of quadratic, trinomial, and rational. We've taken the derivative, found out where it's increasing and decreasing. Also analyzed that first derivative, found out where there's relative maximum, relative minimum. We've also found the second derivative, determined where the function is increasing and decreasing, as well as any points of inflection. I feel like that's quite a lot that calculus has told us, right? Okay? Looking at that homework, you've got 2 quadratics, 2 trinomials, and 2 rationals. I don't feel like that's impossible, especially since we've done all the, we've done several of each one of those, okay? I've got this homework due on Wednesday. Is anybody going to the career day thing on Wednesday?
Oh, I thought it was
It's the 30th.
Oh, it's on Thursday?
Yeah.
Thursday, Wednesday is the 30th.
Oh, then it's
Halloween is on Thursday, the 31st.
I'm pretty sure it's on Thursday.
No,
It's on Wednesday the 30th. I still have the old one, but.
Okay, anyway, if that's the case, then it'll be due for y'all on Thursday, but just make sure you have it done, Okay? Alright, tomorrow, optimization, so you should have notes on that already that you took, yes? I think it's on 4-5, if you haven't taken notes on that. And go ahead and stop the music, I do have your quizzes.